Hello and welcome to Chapter 2, Matrix Algebra. This section 2.1, is over matrix operations, and I think that you will find this to be pretty easy, pretty self-explanatory, because this is a topic that is really taught in algebra courses that you have taken a long time ago. So hopefully this information comes back. But a little bit of things to remind you of. Remember that an m by n matrix has m rows and n columns. And so the number of rows are the vectors in Rm. So matrix A basically can be written in this way, and sometimes we use different notation. If we have a relatively large matrix like this one here, we might refer to a specific entry as A sub ij. So basically I represents the row in which the entry is found, and J is the column. Some definitions that you'll see in this section are found here. Diagonal entries are the entries that, of course, go at a diagonal, and they form the main diagonal of the matrix. A diagonal matrix is a square matrix whose non-diagonal entries are zeros. So everything other than this are zeros in a diagonal matrix. An identity matrix has all ones at the diagonal. Sums and scalar multiples, basically what this is saying is if you add or subtract matrices, they must have the same dimensions, because what you're doing is you are adding or subtracting corresponding entries. So if we're adding these two matrices here, you will add the corresponding entries since we have addition. So in order to do this, you have to have matrices with the same dimensions. Scalar multiplication is done the exact same way. If you have a scalar of 5 here, basically it's the distributive property. So you multiply everything by 5 to get the new matrix. Okay, pretty straightforward. So here is an example. I've given to you 3 different matrices. And remember, when you are finding the dimensions, there are 2 rows and 3 columns here, 2 rows and 3 columns, and 2 rows and 2 columns. So if I want to find matrix A plus B, I will simply add, they have to be the same dimensions, which they're both 2 by 3, so that's great. So I'm just going to add each of the corresponding entries and put it in that same place. So you can pause this, see if you get the same thing. This here is the matrix you should get. Now, in the next example, I want to take matrix A and add it to matrix C. The problem is matrix A is a 2 by 3, and matrix C is a 2 by 2. This is not possible because the matrices have different dimensions. Here we have a scalar multiple of matrix A. So all I'm going to do is take matrix A and multiply each entry by 2 to get the following matrix. Then in this last example, we have 2A, which we just found, minus b. So 2a is this, minus b, which is this. So in this case, we are performing subtraction, so it's important that you make sure each element in matrix B is subtracted. Go ahead and pause this and see if you get the same result, which is this matrix here. Okay, so pretty straightforward. This basically illustrates theorem 1, which is stated here. You can go ahead and read through this, but it was illustrated in the previous example. Now, matrix multiplication is actually a bit more complicated than adding and subtracting and scalar multiplication. So this is basically saying one matrix times another. So this is different than scalar multiplication. So in the past, we introduced the product AX of a matrix and a vector as a linear combination. Then we thought about it as a transformation. And so now what we're going to do is think of it in yet another way, which is the composition of two transformations. And it is illustrated here. So this leads us to the next slide, which provides us our definition, which is written here. So basically, you can take A times each part of B, and then it's multiplication. I think this here sums it up. So each column of the product is a linear combination of columns A, and the weights come from column B. Now, when you are multiplying two matrices, they do not necessarily have to be the same dimensions. Sometimes it's good, but other times it's not. So basically, you need the same number of rows in A as columns in B. And I'll show you how to look at this in a minute. But this here is a good piece of advice. When you're multiplying, it's always the row times the column. And I'll show you an example of that here in a second. So here's what I mean. So this here is saying that matrix A is a 2 by 5 matrix. Matrix B is a 5 by 3 matrix. And I want to know what the sizes are of matrix AB and matrix BA if they're defined. Now, when it comes to matrix multiplication, these two items that I have written are not necessarily equal. So you need to be very cautious. So if I'm looking at this first example, matrix AB, matrix A has the dimensions 2, 5, and matrix B has the dimensions 5 by 3. Because these are equal, we are happy because the number of columns here is equal to the number of rows here. If that is the case, then we can multiply, and our resulting matrix is a 2 by 3 matrix. Let's take a look at BA. So matrix B is a 5 by 3 matrix, and matrix A is a 2 by 5 matrix. Because these are not equal, we cannot multiply these two matrices, and this matrix is not defined. Okay, so that is the check that you'll want to take. Okay, so here's our next example, and I'm basically going to show you two methods to compute matrix AB. Now, the order in which these occurs matters. AB is not the same as matrix BA. Okay, so the order matters. Okay, so this is basically method 1. So what I'll do is I'll define B to be B1, B2, B3, where this represents B1, this represents B2, and this represents B3. So those columns. So what I'll do is I'll find A, B1, which is taking matrix A, times matrix B1, so just that column. This results in the matrix 5, 1. Then I'll take A times B2, so A is this, B2 is the second column. When I multiply these, I get this. And when I'm multiplying, I'm taking this row times this column, this row times this column, and then AB3 is this. So what I've done is I've created the new columns for AB. So together, AB is equal to, the first column is this, the second column is this, and the third column is this, where this is AB1, AB2, and AB3. Okay, so this is the first method that is shown in your text. The next method that I'm going to show you, it's the same exact problem, but it's a different method. Okay, so here it is. This is the method that is primarily taught in most of your early algebra classes. So here's what I want to remind you. If matrix A is a 2 by 2 matrix and matrix B is a 2 by 3 matrix, since these are the same, we can multiply them, and the resulting matrix is going to be a 2 by 3 matrix. So when I calculate AB, I know that my resulting matrix is going to have 2 rows and 3 columns. So sometimes it's helpful to actually write that out. And what I'll do is I always take the rows times the columns. So in order to do that, I'm going to take this row. Since this is the first row, the result will go in the first row. And I'm going to multiply it by each column. And each column I multiply will go in the corresponding column. Okay, so here's what we'll do. We take 2 times 4 and add that to negative 3 times 1. Then I keep using the same row, but I move on to the next column. So 2 times negative 2 plus negative 3 times 0. Same row, last column. 2 times 3 plus negative 3 times 6. Once you have used the first row on all 3 columns, then you can move on to the next row and do the same thing. So the second row, the result goes in the second row. So 0 times 4 plus 1 times 1. Move to the next column. 0 times negative 2 plus 1 times 0. Next column. 0 times 3 plus 1 times 6. Hopefully you notice some patterns here. 2, 2, 2. Negative 3, negative 3, negative 3. 0, 0, 0. 1, 1, 1. And then you just simplify that arithmetic there. So you get 5, 1, negative 4, 0, negative 12, 6. Which is the exact same answer that we got in the previous example using a different method. Okay, so either method is fine. I would say that this is the one that is more commonly used. So if you are going on to teach math in high school, this will be something that you will be teaching. So properties of matrix multiplication is stated here in Theorem 2. I don't think you need me to read that to you. Then here, here is a couple red flags. If AB equals BA, which I've mentioned is not always the case. Sometimes it is, but not always. Then we will say that A and B commute. So typically, they are not equal. Just because AB is equal to AC, it does not mean that matrix B and matrix C are the same. And then finally, if matrix AB results in 0, it does not necessarily mean that matrix A is the 0 matrix or matrix B is the 0 matrix. So now we're going to talk about the transpose of a matrix. So in this first example, it talks about a square matrix, but it does not necessarily have to be a square matrix in order to transpose it. And just a reminder, a square matrix is the number of rows is the same as the number of columns. So 2 by 2, 3 by 3, 4 by 4, so on and so forth. The transpose of some matrix A is written as A, and it looks like an exponent of T, but it's solely notation. And basically what happens is the rows of the first matrix become the columns, or the rows of the matrix become the columns of the transposed matrix. So there's the theorem, of course, which says the transposition of the transposed matrix results in the original. It just kind of shows you some different things. So here is basically what a transposed matrix looks like. So if I want to transpose matrix A, I represent it with this notation. And basically, the rows of this matrix become the columns of the transposed matrix. So row AB becomes column AB. Row CD becomes column CD. If I want to transpose matrix B, then these rows become the columns of this. So negative 5, 1, 2, negative 3, and 4, 0. And finally, this one, these become the columns here and here. And that basically wraps up this section. There really aren't too many homework problems. I think there are, let's see, it looks like 5 homework problems. So I think that you will find this homework is pretty quick. Enjoy!